Hello, today's podcast is about net forces and Newton's second law. First, we're going to learn about net force, its definition, and how we calculate it. Second, we're going to learn Newton's second law of motion. And finally, we're going to learn how to use Newton's second law of motion to analyze force diagrams and net force. First, net force. It's the sum of all the forces acting on an object. So the forces acting in the negative direction cancel, also known as balance, forces acting in the positive direction. The net force is the leftover or unbalanced portion of the forces. It's a vector quantity because it has both magnitude, also known as strength, and direction. So net force is a vector quantity just like all the individual quantities. Let's take a look at an example here. We have a box and we have some vertical forces and horizontal forces. When we go to calculate net force, we have to do it for each dimension separately. So we need to do it for the vertical forces and we need to do it separately for the horizontal forces. So if we look at our vertical forces, we have 10 newtons in the up direction, we have 15 newtons in the negative direction. And so when we add those forces together, we wind up with a net force or leftover force of 5 newtons in the negative direction, in this case pointing down. If we look at our horizontal forces, we have a 10 newton force to the left, the negative direction, and we have a 13 newton force to the right, which is the positive direction. We add those two forces up, and our net force is 3 newtons. That means we have a leftover force, an unbalanced force of 3 newtons pointing to the right. Let's move on and look at Newton's second law of motion. It says an object's acceleration is proportional to the net force acting on the object and inversely proportional to the object's mass. We often see this represented as a math equation. This is the only one of the 3 laws of motion that are represented often by a math equation. And here we have acceleration is equal to the net force divided by the object's mass, or the more common way we'll see it is the net force is equal to the mass times the acceleration. Mathematically, these two are the same thing. Well, what does it mean conceptually? As we increase the net force, the acceleration increases. That makes sense. If we're pushing something and all of a sudden we push it twice as hard, we would expect it to accelerate more, and it does according to Newton's second law. Also, as the mass increases, acceleration decreases. So if you're pushing a box and it's accelerating and all of a sudden somebody puts some more weight on top of it, you're not going to accelerate as fast because the mass has increased and you're not pushing any harder. Let's take a look at how we use Newton's second law mathematically. And here's a problem. If a 10 kilogram box is accelerating at 2 meters per second squared, what is the net force acting on the box? Well, we want to use this version of the equation because it's set up to solve for net force. So we go ahead and plug in our mass of 10 kilograms and our acceleration of 2 meters per second squared, and we find out that the net force is 20 kilograms times meters per second squared. Now we have a special name for this unit. It's called the Newton, and it's abbreviated by capital N, and that's in honor of Sir Isaac Newton. Let's look at one more problem. If a net force of 50 newtons is exerted on the 10 kilogram box in the negative direction, what is the box's acceleration? To solve this problem, we need to use this version of the equation because it's set up to find acceleration. And so we plug in our net force, 50 newtons or 50 kilograms meters per second squared, and we need to remember to put the negative sign in front of it because the force is in the negative direction. We divide it by our mass of 10 kilograms, and our acceleration is 5 meters per second squared in the negative direction. Let's look at how we use Newton's second law to analyze force diagrams. Here we have a force diagram of a horse. We have traction force, the ground pushing the horse to the right. We have a tension force of the cart pulling back on the horse. And we have the force of gravity pulling down on the horse. And we have the ground pushing up with a normal force. We know that these two forces are balanced. The mass of the horse is 440 kilograms, and its acceleration horizontally is 2 meters per second squared in the positive direction. In our previous unit, we learned how to create vertical and horizontal force equations once we drew the force diagrams. So we would have looked at this force diagram and we would have said the equation for the vertical forces is the normal force plus the gravity force, and we set them equal to 0 because they're balanced. But now we would have difficulty with these horizontal forces because we look at them and it would be the tension force plus the traction force, but we can't set them equal to 0 because we know these forces are not balanced. Well, we can use Newton's second law to write force equations regardless of whether the forces are balanced or unbalanced. We start with our basic math equation for Newton's second law, and then we use that for the vertical forces and the horizontal forces. So we look at the force diagram, we just add up the two vertical forces, we set them equal to the mass times the vertical acceleration, and we do the same thing with the horizontal dimension. We add up the horizontal forces, we set that equal to the mass times the horizontal acceleration. Next, we go ahead and plug in the numbers that we know. We know the force of gravity is 4,312 newtons in the negative direction. We know the horse has a mass of 440 kilograms. And because the object is not moving vertically, we know its acceleration vertically is 0 meters per second squared. We do the same thing with the horizontal forces. We know the tension force is 75 newtons in the negative direction, and we know the mass of the horse and the horizontal acceleration is 2 meters per second squared. Then we go ahead and rearrange the equation to find the two forces we don't know. That's the normal force vertically, and horizontally that's the traction force. Then we crunch these numbers in our calculator and we find that the normal force is 4,312 newtons in the positive direction, and the traction force is 955 newtons also in the positive direction. Well, let's look at a problem-solving strategy for using Newton's second law. We'll have two types of problems. The first type, you're given the acceleration and you're asked to find one of the forces. The other type is you're given the net force. In other words, you're given all the force information and you're asked to find the acceleration. In type 1, the first step, we want to draw the force diagram and include all the component forces. Next, we want to use Newton's second law to write the vertical and horizontal force equations. So here we have the net force in the vertical dimension is equal to the sum of all the forces. This symbol is the Greek letter epsilon, and it just means we're adding up all the vertical forces, and they're equal to the mass times the vertical acceleration. We do the same thing in the horizontal dimension. We add up all the horizontal forces, and we set them equal to mass times the horizontal acceleration. Next, we rearrange the equation to solve for the unknown force. And lastly, we plug the values that we know into our equation and we calculate the answer. Now, we use the same process for the other type of problems. It's just that this time we're going to be rearranging the equation to solve for acceleration because we know all the forces. Let's take a look at some specific examples. Here's a type 1 problem with balanced forces. We have a passenger riding in an elevator and it's moving up at a constant velocity of 2.5 meters per second. The passenger has a mass of 85 kilograms, and the question asks us how strong is the force pushing up on the passenger. Well, we go ahead and draw our force diagram showing the gravity force and the normal force, which is the floor pushing up on the passenger. We start with our basic Newton's second law equation, so we add up the vertical forces, Fn plus F sub g, and we set that equal to the mass times the acceleration. Next, we rearrange the equation to solve for the normal force. Then we need to know the force of gravity, so we need to find the weight. So we use our weight equation and find out that the weight of the passenger is 833 newtons. And we can plug that along with its mass and acceleration into our equation up here. The mass of the passenger is 85 kilograms. Because the passenger and elevator are moving at a constant velocity, its acceleration is 0. And we plug in the negative 833 newtons for the force of gravity, and we find out that the normal force is 833 newtons. Now, we learned how to do this type of problem in our last unit, but let's move on. And how do we solve this problem when we have an upward acceleration? So it's the same elevator, same passenger, it's just that now the elevator is accelerating upward at 2 meters per second squared, and we want to find how strong the normal force is. We draw our force diagram. Notice the normal force is larger, so we're going to have a net force pointing up. We take our basic Newton's second law equation and we add up the vertical forces on the left-hand side, and we set them equal to the mass times the acceleration on the right-hand side. We want to rearrange this equation to solve for the normal force. Next, we need to find the weight of the passenger so we can calculate the strength, so we know the strength of the gravity force. Then we go ahead and plug our numbers in. Notice that the normal force is 1003 newtons. So when the elevator is accelerating upward, the normal force is larger than the force of gravity. Let's calculate the normal force when the elevator is accelerating downward. So everything's the same about this problem except the acceleration is 3.0 meters per second squared in the downward direction. First, we want to draw the force diagram, and in this case we see that the normal force is smaller than the gravity force, because if the object's accelerating downward, then the downward pointing force has to be larger. We use our basic formula for Newton's second law. We go ahead and rearrange it to solve for the normal force. We find the weight. Notice in these problems the weight is always the same, and so the force of gravity doesn't change. It's negative 833 newtons. However, our acceleration now is negative 3 meters per second squared, and the mass remains 85 kilograms. When we crunch this in our calculator, we find out that the normal force is 578 newtons. So when the elevator is accelerating downward, the normal force is less than the force of gravity. Let's move on and look at a type 2 problem, and that's where we're given the information about the forces and we need to find the acceleration. Again, it's an elevator problem. This time we have a student who brought their bathroom scale with them, and they enter the elevator, they're standing on the scale, everything's at rest, motionless, and he sees that his weight is 840 newtons. As the elevator starts to rise, the scale reading increases to 1050 newtons, then it returns back to the 840 newtons until the elevator slows to a stop at the 10th floor, and as the elevator is slowing down, the scale reading drops to 588 newtons. And then once the elevator stops, the scale returns back to the normal weight of 840 newtons. Problem's asking us to determine the acceleration at the beginning and end of the trip. Well, here's something we need to know about our bathroom scale. It does not measure our weight. It does not measure the force of gravity. It measures the normal force. Now, when we're not moving and the elevator's not moving, the normal force and the gravity force are balanced. So the 840 newtons is our gravity force, of course in the negative direction. Then we need to use our weight equation and rearrange it to solve for mass, because we need to know the mass of the passenger, and his mass is 85.7 kilograms. Now we can go on and solve the problem. Let's work at the beginning of the ride first. We draw the force diagram. We have our two forces. We know since the elevator is accelerating upward, the normal force is going to be larger than the gravity force. We go ahead and write our vertical force equation. So the normal force plus the gravity force is equal to the passenger's mass times his acceleration vertically. We go ahead and rearrange this equation for acceleration. Then we plug in our normal force, and we know from the problem that when the elevator is accelerating at the beginning of the ride, the normal force is 1050 newtons. We add the gravity force, which is 840 newtons in the negative direction, and divide it by the passenger's mass, and we find out that the elevator's acceleration at the beginning of the ride is 2.45 meters per second squared. Now, to look at the end of the ride, we draw the force diagram. This time the normal force is smaller than the gravity force. We follow the same process we did before, only this time our normal force is not 1050. We see from the problem that the normal force at the end of the ride is 588 newtons. We add that to the force of gravity, negative 840 newtons, divided by the passenger's mass, and we find that the acceleration as we come to the end of the ride is 2.94 meters per second squared in the negative direction. Well, this wraps up what we wanted to learn. Let's briefly summarize what we learned. Net force is the sum of all forces in the vertical and horizontal dimensions. It is the unbalanced part of the forces. It is a vector quantity with both magnitude and direction. Newton's second law of motion tells us that acceleration is proportional to the net force acting on the object and inversely proportional to the mass of the object. It's often stated as a math equation: net force is equal to the mass times the acceleration. We can use Newton's second law to write vertical and horizontal force equations regardless of whether the forces are balanced or unbalanced. And we know that if we're given the acceleration, we can use these force equations to find the strength of the force, and vice versa. If we know the strength of the forces, we can use these equations to find the acceleration. Well, this wraps up our podcast. I hope you found this information helpful, and have a good day.